All right, but as I tried to demonstrate for you in class last time, just because you've heard it a lot doesn't mean you understand it. So what we're going to do is we're going to take another swing at the idea of kinetic and potential energy, system and surroundings, work and heat, and we're actually going to do it through a graphical view. I am a little frustrated to say, I made up these notes several years ago before the 12th edition, before the edition of our book came out. I made up all these diagrams, and then these guys stole the diagrams from me. I think they're actually in chapter 5, and I'm planning on getting a lawyer and suing them. Where are they at? Yeah, and actually theirs are even cooler because theirs are like vaults and stuff, but that's all right. I still am offended. So, okay, so guys, we're going to go through this and we're going to talk about all of these interplays. And then here's what's going to happen, and this is going to sneak up on you. Ready? Here's the way this is going to go. We're going to go system, we're going to go surroundings, we're going to go kinetic and potential energy and their interplay, and then we're going to talk about surroundings and system and work and heat. And then, guys, once we're done nailing down all this idea of all these different relationships, then we're going to get rid of work. Now, guys, track through this with me in your brain. You ready? What are the only two ways for the energy of a system to change? Work and heat. Now, what if we get rid of work? Then what's the only thing that's left? Heat. And, guys, heat in the absence of work has a name. Guess what it is? Enthalpy. Okay? That's it. We're done for the day. Do you want your homework? Because, guys, that's it. That is the Reader's Digest version of the day. We're going to help you understand kinetic potential energy, system surroundings, work, and heat. Then we're going to get rid of work. And heat, in the absence of work, is called enthalpy. Get it? No. But let's help you get it. So, guys, this is the way this all goes down. So in order to dig into this, we are gonna review. I'd encourage you to write this down with me. Look at your system. Go Tigers. It's gold. Now, guys, when we talk about our system, then what does everything else become? The surroundings. Now, here's an interesting thought. What do the system plus the surroundings equal? The universe. Okay, now, focusing upon the system, we understand that all systems contain energy. And what are the two types of energy that make up the energy of a system? Kinetic and potential. Again, remembering that potential energy is energy that is stored in relation to position, and kinetic energy is the energy of movement. Now, we also talked about the idea that the system and the surroundings can exchange energy. But guys, this is important. I hope you're comfortable with the idea that kinetic and potential energy can actually interconvert, right? When did you see that on Wednesday? The ball, the block. As the block fell, potential became kinetic energy, right? But when kinetic and potential energy interconvert, what happens to the overall energy of the system? It don't change, right? So, how then does the energy of the system change? And that's where we now talk about work and heat. How about that for a good little review? Now, guys, as you bring this all together then, you know what? I wish those were white. I think I can make them white. Text. Color. White. Boom. Oh, isn't that better? See, you couldn't see them before. And now, shining like the sun. Oh, huh? All right. Now, guys, as we did this before, we all agreed upon these overarching ideas that you only need to write down if these don't make sense to you. That within a system, energy can interconvert between potential and kinetic with no change in internal energy. So how does internal energy change? Again, the answer is work and heat. And guys, please again remember, this is not dumbed down because this is just AP chemistry. right? For some of you, this is an earth-shattering idea because you thought AP Chemistry was the top of the mountain. Guys, AP Chemistry is still down in the valleys. Actually, AP Chemistry is in a well at the bottom of the valley. Guys, you have no idea. Wait until you get to college and start really digging into this stuff. Oh boy. It is. It's actually down in China. But guys, this is not dumbed down. It doesn't matter how many abbreviations you have after your name. Guys, this is all you got. 2 kinds of energy and 2 ways of changing energy. You guys okay? All right. So guys, with all of that said, now we need to talk about the rules of the game. You ready? Here's one of the rules of the game. The game that we're playing is, let's move energy around. Yeah, here are the rules of the game. It's really not a very fun game. But the reality of it is, you guys all know me well enough to know that if I weren't a teacher, I wouldn't be a chemist. So it's as good as chemistry can get as far as games go. You guys know that about me, right? That I love to teach, but chemistry just happens to be what I know. So guys, first law of thermodynamics. This is actually an accounting rule. And guys, the accounting goes like this. Energy is neither created nor destroyed when changing forms or transferring between a system and surroundings. Guys, good. What I'd like you to do is this. Once you're done writing this down, please circle the words changing and transferring next to or somewhere related to changing and transferring. Please write down everything you know about how that happens. Changing forms, you could circle changing forms if you want. Maybe not just changing. But guys, once you're done writing this down, again, circle changing forms, circle transferring, and then do a little brain dump on your paper about everything that you know about those 2 ideas. Another second. You guys are a good-looking bunch. You know that? No. Just more so today. Most of you showered, which I appreciate. Vanessa's going, no, I kind of didn't. But you chuckled. Yeah, it wasn't me. It was you. You scoffed. She still smells lovely. You guys all done? Okay, brain dumping, guys. What do you know about changing forms? What do you know about transferring? The answer had better be quite a bit. Because guys, once you bring together these ideas of changing form and transferring, then this bigger thought has some pretty significant implications. Can we talk about it? Okay. So guys, let's reread it just for emphasis. First law of thermo says this. Energy is neither created nor destroyed when 2 things, one of 2, or both happen. One is when energy changed forms or when it's transferred between the system and the surroundings. Let's do changing forms first. What do we know about that? What are the 2 kinds of energy? Kinetic and potential energy. What do we call those when they come together? internal energy. And guys, the idea is as kinetic becomes potential or potential becomes kinetic, the internal energy of the system does not change. You okay with that? Now let's move on. Now we talk about the word transferring. And when you read the word transferring, you all wrote down what two words? Work and heat. Now, guys, this becomes significant because now when we go back and reread this, we're saying kinetic and potential can switch, no change in energy. Now we're saying work and heat can happen with no net change in energy. So the amount of energy that is gained by the system is equal to what? The amount of energy lost by the surroundings and vice versa. So now let's wrap our head around this, because guys, the significant implication of what this says is there is a fixed amount of energy in the universe, and all it does is move around. Get it? Because guys, if energy can interconvert, kinetic to potential, and if energy can come and go between the system and the surroundings without being created or destroyed, it means there's a finite amount of energy in the universe. Does all this sound kind of familiar? Sounds like the law of conservation of mass. Well, guys, it turns out that this is a similar concept, the law of conservation of energy. In the same way that mass is conserved, energy is conserved. And last year, I think you wrapped your mind around the idea that there's a finite amount of matter in the universe. What we got is what we got, and all we do is reorganize it, right? You're all okay with that? Well, guys, that's also true of energy. What we've got is what we've got, and all it does is move around. So matter is conserved and energy is conserved. Are y'all comfortable with that? Okay, so let me say this now then. You ready? Because this is where things, you don't need to really keep track of this, but you need to understand this. So you're okay with the idea that energy is conserved in the universe? What we got is what we got. Matter is conserved. What we got is what we got. But guys, here's the thing that's kind of weird. The amount of matter in the universe is not consistent, and the amount of energy in the universe is not actually consistent. They can interconvert. Matter can become energy, and energy can become matter. Says who? Einstein, E equals mc squared. So guys, that's the next layer to this onion that we don't have to get into here, but this is the big idea if you watch my hands. Matter is conserved, right? Law of conservation of mass. Energy is conserved, law of conservation of energy, first law of thermo. So the idea here is that we have a finite amount of matter and a finite amount of energy, but those finite amounts of matter and energy can interconvert in nuclear processes. And that's what E equals mc squared is all about. So we could say this finally once and for all. The total amount of matter and energy combined is actually finite. You get the idea? Okay. Kind of wacky, yeah. We're getting closer to it. Well, yeah, because you're right that there are many interesting, some more nebulous than other ideas about what our universe is really all about. But regardless of if you're adhering to a steady state universe or an expanding universe or an oscillating universe or even multiple parallel universes, we can still come back and say this universe. And to our best understanding, unless something's changed really recently that I'm unaware of, I think most physicists would in fact adhere to the idea that the total amount of matter and energy together is constant. Yes. Well, but infinite size and infinite stuff in it are two different things, right? Do you know what I'm saying? I don't either. But it's kind of Yeah, and that's the problem, is we can still only account for 40% of it anyway, right? So, but for our purposes, we get the idea. Yeah, because it was challenging to me the first time that I was presented with the thought that in the mind of a physicist, matter is condensed energy in the same way that water is condensed steam. That if you have high energy systems, and if you remove energy from them, they can become mass. Which is crazy. Yeah, isn't that wild? Yeah, but yeah, go ahead, Jared. Yeah, these are not chemical, these are nuclear processes. But let's track it the other way, because I think it may make more sense to you. Rather than say, how does energy become matter, how does matter become energy? And then we can talk about the other as well. But that's the magic of probably the thing that's most relevant to you. Is remember last year when we talked about Hiroshima and Nagasaki and those bombs? The idea is that all of that energy that destroyed Hiroshima and Nagasaki was actually matter being converted to energy. They actually, I don't know if I shared this with you, and I think my numbers are good. They actually went back and crunched the numbers and looked at specifically at Hiroshima, and given that big ball of uranium that leveled the city, I think the number is somewhere between 0.8 and like 2.5 grams. Okay, remember a gram is a paperclip. They went back and did the math, and I think it worked out that somewhere between about 1 and 2.5 grams of uranium was all the uranium that was actually converted to energy. That the rest of the uranium was actually just dissipated into the atmosphere, and only between like 1 and 2.5 grams of it was actually converted into energy, and that was the energy that destroyed the city. Yeah, it's really, you can Google it. I think those numbers are right. But that's the idea, is that during nuclear processes, that matter is converted to energy. Now, probably the place where you're most comfortable with the idea of energy becoming matter is the Big Bang. That the thing that banged in the Big Bang, that singularity, was actually a ball, if you will, of energy. And as that expanded, it cooled, and when it finally became cool enough, it was able to condense into matter. Initially protons, neutrons, and electrons, and then it went on for, well, initially quarks, it became those. But as it expanded and cooled, it was able to become matter. So, yeah, pretty crazy. You guys okay? Yeah. Absolutely, because they can interconvert, they're certainly dependent upon other. Yeah, definitely. And some of those connections we don't need to make, but yeah. Do you get the sense that this would be better understood or more easily understood in a Colorado high school where you can smoke dope and it's legal? Yeah. So. Yeah, far out, that's right. But guys, understand that's kind of one of the cool things about science is as you dig deeper and deeper into this, it really becomes, wow, this is amazing. And it's good. You guys okay with the first law of thermo? Okay, so guys, with that said then, we need to sort of bring a finer point to this. So it goes like this. Now we're going to really bring together internal energy. And you guys understand internal energy, which is abbreviated E, is the sum of the kinetic and potential energies within a system. And we write it like this. Energy big E is energy sub K plus energy sub P. So guys, once you catch up with me, we're going to sort of draw a line in the sand together. And if you don't like the line we're about to draw in the sand, I'd love to take this up with you later, but we're not going to do it in class. And maybe for most of you, you wouldn't even know what we're talking about and it wouldn't matter, but we'll try. So guys, here's where we are. This is all not redundant, but we've talked about this. That the internal energy of a system, which we abbreviate E, is the sum of the kinetic and potential energies. You guys okay? Okay. Now, guys, I'm going to lay out a thought for you, And then I'm going to talk about the bigger thought, and then we're going to agree together to not talk about the bigger thought. Okay? So just watch. Here's the thought. Guys, internal energy is tricky. You can't measure it. Write it down. Internal energy is tricky. You cannot directly measure it. So we'll sort of play with why in a minute. But guys, here's the problem, and I just want to lay this out here. And you understand that as an AP chemistry teacher, my job is damage control in many situations, right? I spend a lot of time becoming a student of the curriculum and frankly a student of the test, so that I can streamline what we're doing with that laser-like focus to get you ready for the test. You know what I'm saying? And what that means, guys, is I've got to make some hard choices. What do we need to talk about, and what are we going to let go? Not because it isn't important, but frankly because the return on investment isn't worth it. Guys, thankfully in 2014, they made my job a lot easier, because there was a lot of, forgive me, but there was a lot of crap we didn't talk about in my classes, because I knew it wasn't going to be on the test, and yet it was still in the course outline. Things like three-dimensional crystal structures of salts. When I first started teaching AP chemistry, remember our little green and gray guy over there? We spent 2.5 class periods learning that that is what is called a face-centered cubic structure that has a unit cell composed of 7 objects clustered around. Holy smokes. We took forever learning about crystal structures, and there was one multiple choice question on it on the test. And so finally I got smart and said, we're going to spend that time better elsewhere. You know what I'm saying? In 2014, they just wrote it out of the curriculum because they finally figured out that the good AP teachers weren't teaching it anyway. Okay? So, ready for the term? State function. Do you remember this from looking over chapter 5? State functions? Okay. Guys, bottom line, just briefly, a state function is a state of a system that doesn't depend upon the direction from which you got there. Get it? Me neither. Well, that's not true. I do understand it. But here's the thing. We could spend the next 45 minutes talking about all of these nebulous, you know, hey, what's a state function? Like Joey early asked, hey, what's an open container? What's a closed container? And we talked about it because that was important. Guys, we could spend a pant load of time trying to help you understand state function, and in the end, it doesn't help. So, the bottom line is this. Internal energy is a state function. As a result, you can't directly measure it. You can only measure how you got there. But we're not going to get into that. Guys, what we're going to do is we're going to back away from this, and we're going to say, you know what, for what we're doing, we're going to let that be whatever it is, and we're just going to deal with the ramifications of it as we practically need to be able to do this stuff rather than get into all the deep, ugly, nasty stuff. So guys, if you're really excited about state functions, one, you're weird, but if you're really excited about state functions, the book does a nice job on it. Frankly, the guy at Bozeman Science, have you seen the Bozeman Science videos? Actually, he's a high school teacher up at Bozeman High School, did an amazing series of physics and AP chemistry videos. Look up Bozeman Science. Sadly, he's not teaching there anymore because, as happens with most good teachers, we remove them from the classroom and make them do other things, which makes me wonder why I'm still here. Apparently, I'm not a very good teacher. But guys, this Bozeman Science guy is not there anymore. But look up Bozeman Science state function. He does a great job with it. Bottom line for us is this, guys. Because of the nature of internal energy, and because it doesn't matter. It's a state function, so it doesn't matter how you got there. You just need to know where you are. We, instead of talking about internal energies empirically, we don't have an internal energy meter that we can go poke in something. Oh, hey, look at how much internal energy you have. We can't do that. Sorry, I'm touching you. I'll probably go to jail. But guys, we don't have an internal energy meter. So instead, what we do is we measure changes in internal energy. And now you're going, wait, if you can measure the changes, why can't you measure them directly? Well, guys, think about what happens to substances when we change their internal energy. Think about this with me, and this will help. This will maybe bring this together. So what we're saying is we can't directly measure the internal energy of this block. But what we can do is change the internal energy of the block and watch that change. So guys, ready? I know you're sick of it. How do we change the internal energy of the block? Work and heat. So how do you know I just did work? It moved. So what can we actually measure? Move, right? We can't measure internal energy, but if we can measure how far this thing moved, and if we can measure the resistance working against it, we can then calculate how much work was done on it, and therefore how much its internal energy changed based upon how it changed as the work was done. Get it? Now, what about the other way to change energy? Heat. How do we know that we're changing its heat? What could we measure? Temperature. And again, we can infer the change in internal energy because we can measure how much the kinetic energy changed, well, and the temperature of it changed by, you get the idea, by measuring temperature. So guys, again, the bottom line is this. We ain't got an internal energy meter, but by watching how work and heat change a substance, a system, we can then infer its internal energy as we watch it change, mostly through movement or temperature changes. Yeah, well, let's say good. Yeah, good, Spencer. But not just calculate. Let's say measure and calculate. This is the lab data we can actually collect. We can't collect internal energy, but we can collect mass and velocity or temperature. And from those, we can then do the calculations. Just a second. Go ahead. This is why I don't teach physics. Remember we talked about that? Wait, what? So it's not doing work. Well, unless it's accelerating. Until it, well, yeah, because it would never reach terminal. It doesn't. It's an interesting question, but it's not germane to what we need to do, because then it becomes all this esoteric garbage about can it reach terminal velocity and all these other things, and how does inertia affect work, and go talk to Leosa about it. I'm not trying to make light of the question, but it's not germane to what we're doing. Yeah.
When you were demonstrating, like, by moving and energy, would actually increase the...
Okay, hold on, guys. Wait. Okay. Good on you. You love physics. Don't nitpick me moving a block. There is air resistance. Okay, I should have moved it up and down instead of left and right. Good heavens. Join Science Club. I don't know. Okay. So guys, this then is how we're going to quantify this. And you guys all understand, I love your curiosity and the questions are good. But again, this is why the state of Utah doesn't know I have a minor in physics. The actual reason why I didn't want to teach physics, the thing that makes it so hard, is because everybody thinks they know what they're talking about, because any idiot can throw a block in the air and go, look, it's flying, it's a projectile. But there's so many misconceptions that you just end up spending your days trying to make people less stupid. And I finally gave up on it. The nice thing about chemistry is because none of us have seen atoms, I can tell you guys anything I want and you can't prove me wrong. So You guys good? Oh, yeah, absolutely. All right. So, guys, bottom line then is this. This ties back to the diagram that Everett got me to draw on the board when we were grading homework. The idea then being this. If we can't directly measure energy, and instead what we're going to measure is energy changes, we are then going to talk about changes in energy the same way we talk about changes in anything else. Because you understand, right, that change is always final minus initial, right? Where you end up minus where you started. So, with that said, this is kind of, well, are you guys okay with final minus initial? Okay, so with that said then, we end up with two different possible scenarios. What if the final amount of energy is greater than the initial amount of energy? What happened to the energy of the system? It went up, that makes it positive. Now, conversely, if the final energy is less than the initial energy, that means energy went out of the system, and that would make it negative. Does that sit okay with you? Okay. So now, guys, what I would like you to do is, well, when you're caught up. You caught up? Okay. Okay. How about now? Good? Go over to the top of your notes where you drew your happy little diagram. Okay? And guys, let's take a look at this again. We understand this. You don't need to write it down. Converting kinetic to potential energy and vice versa has no effect on energy. Energy is affected by work and heat. So here we go. Change in energy then. Wait, am I missing a slide? No, it's still there. Okay, so guys, change in energy then is a function of work and heat. So let's bring this in. Here's our system, right? Here's our surroundings. And now, guys, what we're going to do, remember we had these arrows that connected system to surroundings, and what were those? Work and heat. Break them up. And now, guys, what we're going to do is we're going to lend signs to these things. Or maybe what you could do if you already drew the arrows is make them double-headed arrows, and maybe that would work as well. Okay, so now, guys, we need to define one more thought. We are now going to talk about work and heat going in and out. And not only are we going to talk about these conceptually, we're going to lend signage to them. Is work a positive or a negative thing? Is heat a positive or a negative thing? But in order for things to be positive and negative, we need a frame of reference. So guys, we touched on this briefly at the beginning of class on Wednesday. Unlike physics, where do chemists put themselves? In the system. There you are. So guys, our frame of reference is always in the system. So guys, if our frame of reference is always in the system, and we're going to call this side work, ready? Left side is work. If work is coming out of the system, is that a positive or a negative thing? Remember, work changes energy. If work is going out, is that positive or negative as it relates to the energy change for the system? Negative. So if work is going out, that would be negative. And if work is going in, that would be positive. Here, let me zoom into this so you can see. I don't want to. But now you wish they were. See? Exactly. But again, guys, if you've been in physics, this could be flipped in your brain. Because in many physics settings, we think of these as being the opposite, because for the surroundings, as work comes out of the system into the surroundings, the energy of the surroundings goes up. How much does the energy of the surroundings go up? Same as the system goes down, and vice versa. Now guys, what about here with heat? Well, if the surroundings are adding heat to the system, is that positive or negative? Positive, and then the other is negative. Again, guys, the underlying thought is it's always in reference to the system, because we are in the system. You guys good? Yo. All right. So guys, have we done to death internal kinetic potential, work, heat? Okay. So guys, now what we're going to do is we are going to get rid of work. Here comes a term that is so important, I underlined it. You ready? It goes like this. We are now going to talk about enthalpy. You bet. Enthalpy, guys, is going to sound to you a lot like ideal gases. Well, if you remember what ideal gases are. Remember we said that ideal gases don't actually exist, that ideal gases are gases that have particles with mass but no volume and no intermolecular forces, but they're actually a fictitious, simplified system that really don't exist because it makes the math easier. And then you're going to hear about enthalpy and you're going to go, does this really exist or is this just simplified? Because the answer is, this really works. This is not some oversimplification. This is the way the world works. So let's talk about enthalpy. Enthalpy, guys, relies upon an assumption. Enthalpy assumes that chemical reactions take place at constant pressure in open containers. Now guys, you'll notice that parenthetically, I gave you the actual name for an open container. It is called a constant pressure container. Do they? Hi. Oh, thank you. Okay, so guys, this is going to sound a little weird. Do constant pressure containers really exist? No. Does that mean the concept is just sort of la-la land, doesn't really work? No. Because let's make sure you understand what a constant pressure container is. So here's what it all boils down to. You ready? Work. So guys, two ways energy get in and out of the system are heat and work, right? How do reactions do work? We touched on it briefly last time. How do reactions do work? Watch my hands. They expand, right? But guys, remember, and you're going to like this because it's kind of like your question earlier. Guys, remember, in order to do work, it not only involves movement, what else has to be there? Resistance, okay? So, keep this in mind. You ready? In order to do work, there has to be movement, listen carefully, movement like expansion, and there has to be resistance. Okay, so how can we keep reactions from doing work? Well, we can get rid of expansion or we can get rid of resistance. Now, expansion we can't really control. If a reaction's going to expand, it's going to expand. So what do? We get rid of resistance. Now guys, watch. This is where this gets weird. How do we get rid of resistance? We imagine that there is a hypothetical, fictitious container that can magically expand and contract at exactly the right rate to get out of the way of what the reaction is doing. Get it? So imagine that you had a balloon, and in the balloon we put some baking soda. Some of you have done this. Put some baking soda in the balloon and then pour in some vinegar and tie it up really tight. What does that reaction do? You'd better know. Releases carbon dioxide in water, right? And so it releases carbon dioxide, and as the carbon dioxide is released, what happens to the balloon? It gets bigger. Is the reaction doing work? Yes. Why? Because the balloon is springy, and you know this from blowing up in a balloon. You've got to do work to get the balloon to blow up, because the balloon doesn't want to blow up. It offers resistance. As you blow it up, you're doing work, right? Now, Imagine that this balloon became a magic balloon that would just magically get bigger at exactly the same rate that the carbon dioxide is expanding and being evolved, and it gets bigger all at once, and then if the reaction was to do something to get smaller, it would close down at exactly the same rate, and it would expand and contract perfectly reflexively so that there's never any resistance to the expansion of the reaction. Is that possible? Not really. But if it were possible, what would happen to work? It would go away. Now, guys, I know that you're now thinking, wait a minute, because this doesn't exist, is this all just hypothetical? And the answer is no. And here's the way we handle this. This is what you've got to understand. These magic containers that get out of the way, like our magic balloon, they are called a constant pressure container, okay? But you don't have to know that term. You can call it an open container, and that's just fine. So guys, in your notes, define for me what an open container is. What is an open container? Given what you understand, what is an open container? So guys, oh, go ahead. Oh boy. Yeah, and we'll talk about it in a second. Okay guys, so what was the critical term that you needed in your definition for an open container? No resistance. So guys, the bottom line is this. It's up on the board. An open container is a hypothetical container which offers no resistance to expansion or contraction. So now we need to ask the so what question. So what? Why is that important? What does it do to our understanding of reactions? I don't ask it hypothetically. So what? What does that do? Gets rid of work. Therefore, and guys, if you don't know that this is the mathematical symbol for therefore, you should learn that, because you're going to be developing logical arguments throughout the year in order to answer AP questions. And logical arguments are based upon therefores. This is true, therefore this is true, therefore this is true. So if you want to save yourself some writing, learn the little three-dotted triangle, which means therefore. Okay, therefore, guys, no work is exchanged. Now, guys, here comes the really big therefore. Therefore, if you can't do work, what are you left with for the only avenue to exchange energy between the system and the surroundings? Heat. And what do we call heat when there can't be work? Enthalpy. Get the idea? It's that simple. So guys, Everett asked an interesting question. He said, can you have an open container in a closed system? Absolutely. Because guys, what does a closed system mean? Energy can get in and out, but matter can't. Now what does it mean that it's an open container? What can it do? Work. So guys, watch, pull that together. Closed system. Can energy get in and out? Can matter? No. How does energy get in and out? Work and heat. Now, if it's an open container, no resistance, so what goes away? Work. Now we're only left with heat. So in a closed system that is an open container, the only way energy can get in and out is heat, which we call enthalpy. Good? Is that okay? Everett, that okay? You're good? Okay, all right. So, guys, all of this to say then, the only way that energy can get in and out is through heat. So, we said this, change in energy is work and heat. But if we can't do work, the thing that we're left with is heat. Now, guys, now we need to switch between heat and enthalpy. Ready? What is Q the abbreviation for? Heat. Enthalpy is not abbreviated Q. So let's get into enthalpy. So guys, enthalpy is heat in the absence of work, or heat that is exchanged under constant pressure. Now guys, here's the thing that's really nice. If you're doing reactions that don't give off gases, you don't even have to worry about the open container. They're not trying to expand anyway. Getting into the gases makes it a little more weird, but we don't have to worry about the subtleties. So guys, heat in the absence of work is enthalpy. Now, enthalpy is abbreviated H. And of course that makes sense, because if work is Q, then certainly enthalpy would be H. Sure. Hey, but at least work is W, right? Got that going for us. Right. Okay, so now guys, what we're going to talk about is we're going to talk about changes in enthalpy. We just talked about changes in internal energy, heat and work, but now that work is gone, let's talk about changes in enthalpy. Well guys, change is still the same. Here's the problem. You're going to start reading this changes in heat because H looks like heat. Heat is Q. This is change in enthalpy. That makes it even worse, doesn't it? Don't ask why. Ours is not to question. Where's that from? Is that biblical? It's either that or Shakespeare. I don't know. All right. So guys, what about this then? Because I remember Everett brought us to this last time in class. Now is where endo and exothermic plugs in. I seem to remember Everett was trying to also connect this to work, or somehow, I don't remember. But guys, now this comes together. When we get rid of work, and when we're only then left with heat, then if we have positive delta H's, meaning that enthalpy is going up, that's endothermic. We're taking in heat in the absence of work. Similarly, if we have negative delta H's, that's exothermic because heat is being given off. Now we actually understand what endo and exothermic means. I know that's pretty significant for y'all. Yeah?
Maybe it'll be a lot more slides because I'm running out of paper. I'd like to do this one paper.
What if I just stop here so you don't run out of space?
Is that the last one?
No. You may have to go with page due. All right, so guys, we are ready to wrap up. You good with endo and exothermic? Okay, so guys, bottom line is this. You ready? Let's make a connection. We are now going to take this and we are going to apply it to chemical reactions. You ready? So we understand that change is final minus initial. But when we tie that to a chemical reaction, what do we call the final stuff in a reaction? Products. What do we call the initial stuff? Reactants. So this makes sense, right? So if we know the enthalpy of the products, and if we know the enthalpy of the reactants, if we subtract one from the other, it'll give us the enthalpy change for the reaction. That makes sense? Okay, so let me show you an example. These are what are called thermochemical equations. An example, you can write it down if you'd like, looks like this. Diatomic hydrogen and diatomic oxygen reacting together to form water. It's a synthesis reaction. It's balanced. It's familiar. But now we got this little thing hanging off to the side. Delta H is equal to negative 483.6 kilojoules. What on earth does that mean? And maybe importantly, where on earth did that come from? So let's talk about both. So guys, let's first of all talk about what this means. So let's sort of parse this. What does delta H mean? Change in enthalpy. Change in enthalpy for what? The reaction. But now we need to define our system. And guys, you got to understand that in a chemistry class, our system is almost always the atoms that make up a reaction. So our system is the hydrogens, oxygens, and resulting water molecules. So that's our system. So now what do we learn from this? Well, first of all, when this reaction takes place, does it give off or take in energy? How do you know give off? Because it's negative. But also, one of you went, this explodes. Guys, when hydrogen and oxygen react together to make water, it explodes. For some of you, it went boop. Remember when you stuck the hydrogen and oxygen you stuck in the burning splint in lab last year and it went boop? That's this. That boop was the delta H. That was the energy being given, went boop, that was that, right? Of course, that wasn't 483 kilojoules because you didn't have 2 moles of hydrogen and 1 mole of oxygen. If you had, it would have been lights out. But guys, how much is 2 moles of hydrogen? 44.8 liters, right? 22.4 is a mole times 2. So if you'd had 48 liters of hydrogen and 22.4 liters of oxygen and gone boop, it wouldn't have been boop, it would have been boom, right? But guys, that's what this is representing. Whether it's a boop or a boom, the negative tells us that energy is going out. Now, the question becomes this: when does this give off 480 kilojoules of energy? And the answer is when we've got 2 moles of this and 1 mole of that. Now, what if we've got 4 moles of hydrogen and 2 moles of oxygen? Double it. Guys, it's important that you understand that these energy values are for the reaction as written. So 2 moles of this, 1 mole of that, 480 kilojoules of energy come out. These are always as written. Now guys, here's an interesting follow-up question. Where do these numbers come from? From actually doing the reactions. And if you're in lab, we're going to start doing these after you're done filtering your silver chlorides. And guys, we are actually going to do these things and learn through a process called calorimetry where these numbers come from. Okay? All right. So guys, what are we going to do with all of this? Let me show you. First of all, there are some rules, and we talked about all of them. I would encourage you to write these, or not write them down, print the notes. Guys, we talked about this though. The more stuff there is, the more energy is released. These are always written as moles represented. But guys, the other thing you need to know is this. If we flip the arrow over, all we have to do is change the sign. So it makes sense, right? To turn water into hydrogen and oxygen, we would have to add energy, which would make this positive. So if we reverse the reaction, we change the sign. That's all you have to do. All right. So guys, what you're going to see, and we actually only have a couple minutes left, what you're going to see in homework, and I'm going to let you fiddle with these, is that we can actually take reactions like this and we can do math with them through dimensional analysis. You can actually figure out how much heat is released when you burn, for example, 4.5 grams of methane. I'll let you look at these in homework, and I think you'll figure them out just by looking at the answers and sort of muscling through them. If we need to talk about them on Tuesday, we can. So guys, that's our day. Let me show you your homework. Goes like this. We will look at these on Tuesday. Have a safe weekend. Before you leave, if you guys all want to exchange phone numbers and get together over the weekend so you can talk about what happens to things falling through vacuums and stuff like that, feel free to do that. I recommend Mountain Dew and pizza.